Hilbert space. In mathematics, Hilbert spaces named for David Hilbert allow generalizing the methods of linear algebra and calculus from the finite-dimensional Euclidean spaces to spaces that may not have a finite dimension. A Hilbert space is a vector space equipped with an inner product which allows defining a distance function so that it becomes a complete metric space. They serve as a first template for extending the differential and integral calculus that is normally done in Rn, though this can be done more generally using normed spaces. Hilbert spaces arise naturally and frequently in mathematics and physics, typically as infinite-dimensional function spaces. The earliest Hilbert spaces were studied from this point of view in the first decade of the 20th century by David Hilbert, Erhard Schmidt, and Frigyes Riesz. They are indispensable tools in the theories of partial, differential equations, quantum mechanics, Fourier analysis, which includes applications to signal processing and heat transfer, and ergodic theory, which forms the mathematical underpinning of thermodynamics. John von Neumann coined the term Hilbert space for the abstract concept that underlies many of these diverse applications. The success of Hilbert space methods ushered in a very fruitful era for functional analysis. Apart from the classical Euclidean spaces, examples of Hilbert spaces include spaces of square-integrable functions, spaces of sequences, Sobolev spaces consisting of generalized functions, and Hardy spaces of holomorphic functions. Geometric intuition plays an important role in many aspects of Hilbert space theory. Exact analogues of the Pythagorean theorem and parallelogram law hold in a Hilbert space. At a deeper level, perpendicular projection onto a subspace, the analog of dropping the altitude of a triangle, plays a significant role in optimization problems and other aspects of the theory. An element of a Hilbert space can be uniquely specified by its coordinates with respect to a set of coordinate axes and orthonormal basis, in analogy with Cartesian coordinates in the plane. When that set of axes is countably infinite, the Hilbert space can also be usefully thought of in terms of the space of infinite sequences that are square-summable. The latter space is often, in the older literature, referred to as the Hilbert space. Linear operators on a Hilbert space are likewise fairly concrete objects. In good cases, they are simply transformations that stretch the space by different factors in mutually perpendicular directions in a sense that is made precise by the study of their spectrum. Definition and illustration. Motivating example: Euclidean vector space. One of the most familiar examples of a Hilbert space is the Euclidean vector space consisting of three-dimensional vectors, denoted by R3, and equipped with the dot product. The dot product takes two vectors x and y and produces a real number x, y. If x and y are represented in Cartesian coordinates, then the dot product is defined by: the dot product satisfies the properties. It is symmetric in x and y, x, y equals y, x. It is linear in its first argument, axon plus bx2, y equals axon, y plus bx2, y for any scalars a, b, and vectors zone x2 and y. It is positive definite for all vectors x, x equals 0, with equality if and only if x equals 0. An operation on pairs of vectors that, like the dot product, satisfies these three properties is known as a real inner product. A vector space equipped with such an inner product is known as a real inner product space. Every finite-dimensional inner product space is also a Hilbert space. The basic feature of the dot product that connects it with Euclidean geometry is that it is related to both the length or norm of a vector, denoted x, and to the angle th between two vectors x and y by means of the formula. Multivariable calculus in Euclidean space relies on the ability to compute limits and to have useful criteria for concluding that limits exist. A mathematical series consisting of vectors in R3 is absolutely convergent provided that the sum of the lengths converges as an ordinary series of real numbers. Just as with a series of scalars, a series of vectors that converges absolutely also converges to some limit vector L in the Euclidean space, in the sense that this property expresses the completeness of Euclidean space, that a series that converges absolutely also converges in the ordinary sense. Hilbert spaces are often taken over the complex numbers. The complex plane denoted by C is equipped with a notion of magnitude, the complex modulus Z, which is defined as the square root of the product of Z with its complex conjugate. If Z equals X plus E is a decomposition of Z into its real and imaginary parts, then the modulus is the usual Euclidean two-dimensional length. The inner product of a pair of complex numbers Z and W is the product of Z with the complex conjugate of W, W, U, U. This is complex valued. The real part of Z, W gives the usual two-dimensional Euclidean dot product. A second example is the space C2, whose elements are pairs of complex numbers Z equals zone C2. Then the inner product of Z with another such vector W equals 1, W2 is given by the real part of Z. W is then the two-dimensional Euclidean dot product. This inner product is Hermitian symmetric, which means that the result of interchanging Z and W is the complex conjugate. Definition and definition. Second example, sequence spaces. The sequence space L2 consists of all infinite sequences Z equals zone Z2 of complex numbers such that the series converges. The inner product on L2 is defined by, with the latter series converging as a consequence of the Cauchy-Schwarz inequality and the convergence of the previous series. Completeness of the space holds provided that whenever a series of elements from L2 converges absolutely in norm, then it converges to an element of L2. The proof is basic in mathematical analysis and permits mathematical series of elements of the space to be manipulated with the same ease as series of complex numbers or vectors in a finite-dimensional Euclidean space. History. Examples. Libesque spaces. Libesque spaces are function spaces associated to measure spaces X, M, where X is a set, M is a S-algebra of subsets of X, and M is a countably additive measure on M. Let L2X M be the space of those complex-valued measurable functions on X for which the Libesque integral of the square of the absolute value of the function is finite, i.e., and where functions are identified if and only if they differ only on a set of measure 0. The inner product of functions f and g in L2X M is then defined as defined as or where the second form conjugation of the first element is commonly found in the theoretical physics literature. For f and g in L2, the integral exists because of the Cauchy-Schwarz inequality and defines an inner product on this space. Equipped with this inner product, L2 is in fact complete. The Lebesgue integral is essential to ensure completeness on domains of real numbers. For instance, not enough functions are Riemann integrable. The Lebesgue spaces appear in many natural settings. The spaces L2R and L2On of square-integrable functions with respect to the Lebesgue measure on the real line and unit interval, respectively, are natural domains on which to define the Fourier transform and Fourier series. In other situations, the measure may be something other than the ordinary Lebesgue measure on the real line. For instance, if W is any positive measurable function, the space of all measurable functions f on the interval 0, 1 satisfying is called the weighted L2 space L2 0, 1, and W is called the weight function. The inner product is defined by the weighted space L2 0, 1 is identical with the Hilbert space L2 0, 1, M, where the measure M of a Lebesgue measurable set is defined by weighted L2 spaces like this are frequently used to study orthogonal polynomials because different families of orthogonal polynomials are orthogonal with respect to different weighting functions. Sobolev spaces. Sobolev spaces, denoted by HS or WS2, are Hilbert spaces. These are a special kind of function space in which differentiation may be performed, but that, unlike other Banach spaces, such as the Holder spaces, support the structure of an inner product. Because differentiation is permitted, Sobolev spaces are a convenient setting for the theory of partial differential equations. They also form the basis of the theory of direct methods in the calculus of variations. For S a non-negative integer and O, Rn the Sobolev space HSO contains L2 functions whose weak derivatives of order up to S are also L2. The inner product in HSO is where the dot indicates the dot product in the Euclidean space of partial derivatives of each order. Sobolev spaces can also be defined when S is not an integer. Sobolev spaces are also studied from the point of view of spectral theory, relying more specifically on the Hilbert space structure. If O is a suitable domain, then one can define the Sobolev space HSO as the space of Bessel potentials, roughly. Here D is the Laplacian, and 1ds/2 is understood in terms of the spectral mapping theorem. Apart from providing a workable definition of Sobolev spaces for non-integer S, this definition also has particularly desirable properties under the Fourier transform that make it ideal for the study of pseudo-differential operators. Using these methods on a compact Riemannian manifold, one can obtain, for instance, the Hodge decomposition, which is the basis of Hodge theory. Spaces of holomorphic functions. Hardy spaces. The Hardy spaces are function spaces arising in complex analysis and harmonic analysis, whose elements are certain holomorphic functions in a complex domain. Let U denote the unit disk in the complex plane. Then the Hardy space H2U is defined as the space of holomorphic functions F on U such that the means remain bounded for R1. The norm on this Hardy space is defined by I and by. Hardy spaces in the disk are related to Fourier series. A function f is in H2U if and only if, where, thus H2U consists of those functions that are L2 on the circle, and whose negative frequency Fourier coefficients vanish. Bergman spaces. The Bergman spaces are another family of Hilbert spaces of holomorphic functions. Let D be a bounded open set in the complex plane or a higher dimensional complex space, and let L2, HD be the space of holomorphic functions f and d that are also in L2D in the sense that, where the integral is taken with respect to the Libesque measure in D clearly L2, HD is a subspace of L2D. In fact, it is a closed subspace and so a Hilbert space in its own right. This is a consequence of the estimate valid on compact subsets K of D, that have D, that have D, that, which in turn follows from Cauchy's integral formula. Thus, convergence of a sequence of holomorphic functions in L2D implies also compact convergence, and so the limit function is also holomorphic. Another consequence of this inequality is that the linear functional that evaluates a function f at a point of D is actually continuous on L2 HD. The Riesz representation theorem implies that the evaluation functional can be represented as an element of L2 HD. Thus, for every z d, there is a function as L2 HD such that, for all f L2 HD, the integrand is known as the Bergman kernel of D. This integral kernel satisfies a reproducing property He. A Bergman space is an example of a reproducing kernel Hilbert space, which is a Hilbert space of functions along with a kernel Kz, Z that verifies a reproducing property analogous to this one. The Hardy space H2D also admits a reproducing kernel, known as the Seago kernel. Reproducing kernels are common in other areas of mathematics as well. For instance, in harmonic analysis, the Poisson kernel is a reproducing kernel for the Hilbert space of square-integrable harmonic functions in the unit ball. That the latter is a Hilbert space at all is a consequence of the mean value theorem for harmonic functions. Applications. Many of the applications of Hilbert spaces exploit the fact that Hilbert spaces support generalizations of simple geometric concepts like projection, and change of basis from their usual finite-dimensional setting. In particular, the spectral theory of continuous self-adjoint linear operators on a Hilbert space generalizes the usual spectral decomposition of a matrix, and this often plays a major role in applications of the theory to other areas of mathematics and physics. Sturm-Liouville theory. In the theory of ordinary differential equations, spectral methods on a suitable Hilbert space are used to study the behavior of eigenvalues and eigenfunctions of differential equations. For example, the Sturm-Liouville problem arises in the study of the harmonics of waves in a violin string or a drum, and is a central problem in ordinary differential equations. The problem is a differential equation of the form for an unknown function y on an interval a b satisfying general homogeneous Robin boundary conditions. The functions p, q, and w are given in advance, and the problem is to find the function y and constants L for which the equation has a solution. The problem only has solutions for certain values of L, called eigenvalues of the system, and this is a consequence of the spectral theorem for compact operators applied to the integral operator defined by the Green's function for the system. Furthermore, another consequence of this general result is that the eigenvalues L of the system can be arranged in an increasing sequence tending to infinity. Partial differential equations. Hilbert spaces form a basic tool in the study of partial differential equations. For many classes of partial differential equations, such as linear elliptic equations, it is possible to consider a generalized solution known as a weak solution by enlarging the class of functions. Many weak formulations involve the class of Sobolev functions, which is a Hilbert space. A suitable weak formulation reduces to a geometrical problem. For linear elliptic equations, one geometrical result that ensures unique solvability for a large class of problems is the Lax-Milgram theorem. This strategy forms the rudiment of the Galerkin method of finite element method for numerical solution of partial differential equations. A typical example is the Poisson equation do equals G with Dirichlet boundary conditions in a bounded domain O in R2. The weak formulation consists of finding a function u such that, for all continuously differentiable functions v in O vanishing on the boundary, this can be recast in terms of the Hilbert space H10O consisting of functions u such that u, along with its weak partial derivatives, are square-integrable on O and vanish on the boundary. The question then reduces to finding u in this space such that for all v in this space, where a is a continuous bilinear form and b is a continuous linear functional, given respectively by. Since the Poisson equation is elliptic, it follows from Poincare's inequality that the bilinear form is coercive. The Lax-Milgram theorem then ensures the existence and uniqueness of solutions of this equation. Hilbert spaces allow for many elliptic partial differential equations to be formulated in a similar way, and the Lax-Milgram theorem is then a basic tool in their analysis. With suitable modifications, similar techniques can be applied to parabolic partial differential equations and certain hyperbolic partial differential equations. Ergodic theory. The field of ergodic theory is the study of the long-term behavior of chaotic dynamical systems. The prototypical case of a field that ergodic theory applies to is thermodynamics, in which though the microscopic state of a system is extremely complicated, it is impossible to understand the ensemble of individual collisions. The laws of thermodynamics are assertions about such average behavior. In particular, one formulation of the Zeroff law of thermodynamics asserts that over sufficiently long time scales, the only functionally independent measurement that one can make of a thermodynamic system in equilibrium is its total energy in the form of temperature. An ergodic dynamical system is one for which, apart from the energy measured by the Hamiltonian, there are no other functionally independent conserved quantities on the phase space. More explicitly, suppose that the energy E is fixed, and let OE be the subset of the phase space consisting of all states of energy E and energy surface, and let TD denote the evolution operator on the phase space. The dynamical system is ergodic if there are no continuous non-constant functions on OE such that, for all W on OE and all time t, Liouville's theorem implies that there exists a measure M on the energy surface that is invariant under the time translation. As a result, time translation is a unitary transformation of the Hilbert space L2 OE, M consisting of square-integrable functions on the energy surface OE with respect to the inner product. The von Neumann mean ergodic theorem states the following. If it is a strongly continuous one-parameter semigroup of unitary operators on a Hilbert space H, and P is the orthogonal projection onto the space of common fixed points of x, hx equals x t0, then for an ergodic system, the fixed set of the time evolution consists only of the constant functions. So the ergodic theorem implies that is, the long-time average of an observable f is equal to its expectation value over an energy surface. Fourier analysis. One of the basic goals of Fourier analysis is to decompose a function into a possibly infinite linear combination of given basis functions, the associated Fourier series. The classical Fourier series associated to a function f defined on the interval 0, 1 is a series of the form where the example of adding up the first few terms in a Fourier series for a sawtooth function is shown in the figure. The basis functions are sine waves with wavelengths L/n for integer and shorter than the wavelength L of the sawtooth itself except for n equals 1, the fundamental wave. All basis functions have nodes at the nodes of the sawtooth, but all but the fundamental have additional nodes. The oscillation of the summed terms about the sawtooth is called the Gibbs phenomenon. A significant problem in classical Fourier series asks in what sense the Fourier series converges, if at all, to the function f. Hilbert space methods provide one possible answer to this question. The functions nth equals etwapnth form an orthogonal basis of the Hilbert space L20, 1. Consequently, any square-integrable function can be expressed as a series, and moreover, this series converges in the Hilbert space sense, that is, in the L2 mean. The problem can also be studied from the abstract point of view. Every Hilbert space has an orthonormal basis, and every element of the Hilbert space can be written in a unique way as a sum of multiples of these basis elements. The coefficients appearing on these basis elements are sometimes known abstractly as the Fourier coefficients of the element of the space. The abstraction is especially useful when it is more natural to use different basis functions for a space such as L20, 1. In many circumstances, it is desirable not to decompose a function into trigonometric functions, but rather into orthogonal polynomials or wavelets, for instance, and in higher dimensions into spherical harmonics. For instance, if n are any orthonormal basis functions of L20, 1, then a given function in L20, 1 can be approximated as a finite linear combination. The coefficients edge are selected to make the magnitude of the difference ffn2 as small as possible. Geometrically, the best approximation is the orthogonal projection of f onto the subspace consisting of all linear combinations of the edge, and can be calculated by that this formula minimizes the difference ffn2 as a consequence of Bessel's inequality and Parseval's formula. In various applications to physical problems, a function can be decomposed into physically meaningful eigenfunctions of a differential operator, typically the Laplace operator. This forms the foundation for the spectral study of functions, in reference to the spectrum of the differential operator. A concrete physical application involves the problem of hearing the shape of a drum, given the fundamental modes of vibration that a drumhead is capable of producing. Can one infer the shape of the drum itself? The mathematical formulation of this question involves the Dirichlet eigenvalues of the Laplace equation in the plane that represent the fundamental modes of vibration, in direct analogy with the integers that represent the fundamental modes of vibration of the violin string. Spectral theory also underlies certain aspects of the Fourier transform of a function. Whereas Fourier analysis decomposes a function defined on a compact set into the discrete spectrum of the Laplacian which corresponds to the vibrations of a violin string or drum, the Fourier transform of a function is the decomposition of a function defined on all of Euclidean space into its components in the continuous spectrum of the Laplacian. The Fourier transformation is also geometrical, in a sense made precise by the Plancherel theorem that asserts that it is an isometry of one Hilbert space, the time domain, with another, the frequency domain. This isometry property of the Fourier transformation is a recurring theme in abstract harmonic analysis, since it reflects the conservation of energy for the continuous Fourier transform, as evidenced, for instance, by the Plancherel theorem for spherical functions occurring in noncommutative harmonic analysis. Quantum mechanics. In the mathematically rigorous formulation of quantum mechanics developed by John von Neumann, the possible states, more precisely, the pure states of a quantum mechanical system, are represented by unit vectors called state vectors residing in a complex separable Hilbert space, known as the state space, well defined up to a complex number of norm 1, the phase fact. In other words, the possible states are points in the projectivization of a Hilbert space, usually called the complex projective space. The exact nature of this Hilbert space is dependent on the system. For example, the position and momentum states for a single non-relativistic spin-zero particle is the space of all square-integrable functions, while the states for the spin of a single proton are unit elements of the two-dimensional complex Hilbert space of spinners. Each observable is represented by a self-adjoint linear operator acting on the state space. Each eigenstate of an observable corresponds to an eigenvector of the operator, and the associated eigenvalue corresponds to the value of the observable in that eigenstate. The inner product between two state vectors is a complex number known as a probability amplitude. During an ideal measurement of a quantum mechanical system, the probability that a system collapses from a given initial state to a particular eigenstate is given by the square of the absolute value of the probability amplitudes between the initial and final states. The possible results of a measurement are the eigenvalues of the operator, which explains the choice of self-adjoint operators, for all the eigenvalues must be real. The probability distribution of an observable in a given state can be found by computing the spectral decomposition of the corresponding operator. For a general system, states are typically not pure, but instead are represented as statistical mixtures of pure states, or mixed states, given by density matrices, self-adjoint operators of trace 1 on a Hilbert space. Moreover, for general quantum mechanical systems, the effects of a single measurement can influence other parts of a system in a manner that is described instead by a positive operator-valued measure. Thus, the structure both of the states and observables in the general theory is considerably more complicated than the idealization for pure states. Color perception. Any true physical color can be represented by a combination of pure spectral colors. As physical colors can be composed of any number of spectral colors, the space of physical colors may aptly be represented by a Hilbert space over spectral colors. Humans have three types of cone cells for color perception, so the perceivable colors can be represented by three-dimensional Euclidean space. The many-to-one linear mapping from the Hilbert space of physical colors to the Euclidean space of human perceivable colors explains why many distinct physical colors may be perceived by humans to be identical, e.g., pure properties. Pythagorean identity. Two vectors u and v in a Hilbert space H are orthogonal when uv equals 0. The notation for this is u, v. More generally, when S is a subset in H, the notation u, S means that u is orthogonal to every element from S. When u and v are orthogonal, one has one has one has one has one has gonal, one has one has one has by induction on N. This is extended to any family you own on of n orthogonal vectors, whereas the Pythagorean identity as stated is valid in any inner product space Completeness is required for the extension of the Pythagorean identity to series. A series suc of orthogonal vectors converges in H if and only if the series of squares of norms converges, and, furthermore, the sum of a series of orthogonal vectors is independent of the order in which it is taken. Parallelogram, identity, and polarization. By definition, every Hilbert space is also a Banach space. Furthermore, in every Hilbert space the following parallelogram identity holds. Conversely, every Banach space in which the parallelogram identity holds is a Hilbert space, and the inner product is uniquely determined by the norm by the polarization identity. For real Hilbert spaces, the polarization identity is. For complex Hilbert spaces, it is. The parallelogram law implies that any Hilbert space is a uniformly convex Banach space. Best approximation. This subsection employs the Hilbert projection theorem. If C is a non-empty closed convex subset of a Hilbert space H and X a point in H, there exists a unique point Y, C, that minimizes the distance between X and points in C. This is equivalent to saying that there is a point with minimal norm in the translated convex set D equals Cx. The proof consists in showing that every minimizing sequence Dn, D is Cauchy using the parallelogram identity, hence converges using completeness to a point in D that has minimal norm. More generally, this holds in any uniformly convex Banach space. When this result is applied to a closed subspace F of H, it can be shown that the point Y, F closest to X, is characterized by this point Y is the orthogonal projection of X onto F, and the mapping PF XY is linear C orthogonal complements and projections. This result is especially significant in applied mathematics, especially numerical analysis, where it forms the basis of least squares methods. In particular, when F is not equal to H, one can find a non-zero vector V orthogonal to F select X, F and V equals XY. A very useful criterion is obtained by applying this observation to the closed subspace F generated by a subset S of H. A subset S of H spans a dense vector subspace if and only if the vector 0 is the sole vector V, H orthogonal to S. Duality. Weakly convergent sequences. In a Hilbert space H, a sequence Xn is weakly convergent to a vector X H when and H when for every V H. For example, any orthonormal sequence Fn converges weakly to 0 as a consequence of Bessel's inequality. Every weakly convergent sequence Xn is bounded by the uniform boundedness principle. Conversely, every bounded sequence in a Hilbert space admits weakly convergent subsequences, a Leglos theorem. This fact may be used to prove minimization results for continuous convex functionals in the same way that the Bolzano-Weierstrass theorem is used for continuous functions on Rd. Among several variants, one simple statement is as follows. If f(hr) is a convex continuous function such that fx tends to plus, when x tends to, then f admits a minimum at some point x0, h. This fact and its various generalizations are fundamental for direct methods in the calculus of variations. Minimization results for convex functionals are also a direct consequence of the slightly more abstract fact that closed-bounded convex subsets in a Hilbert space H are weakly compact. The existence of weakly convergent subsequences is a special case of the Eberlein-Smulian theorem. Banach space properties. Any general property of Banach spaces continues to hold for Hilbert spaces. The open mapping theorem states that a continuous surjective linear transformation from one Banach space to another is an open mapping, meaning that it sends open sets to open sets. A corollary is the bounded inverse theorem that a continuous and bijective linear function from one Banach space to another is an isomorphism, that is, a continuous linear map whose inverse is also continuous. This theorem is considerably simpler to prove in the case of Hilbert spaces than in general Banach spaces. The open mapping theorem is equivalent to the closed graph theorem which asserts that a linear function from one Banach space to another is continuous if and only if its graph is a closed set. In the case of Hilbert spaces, this is basic in the study of unbounded operators, see closed operator. The geometrical Hahn-Banach theorem asserts that a closed convex set can be separated from any point outside it by means of a hyperplane of the Hilbert space. This is an immediate consequence of the best approximation property. If y is the element of a closed convex set F closest to x, then the separating hyperplane is the plane perpendicular to the segment xy passing through its midpoint. Operators on Hilbert spaces. Bounded operators. Unbounded operators. Unbounded operators are also tractable in Hilbert spaces and have important applications to quantum mechanics. An unbounded operator T on a Hilbert space H is defined as a linear operator whose domain dt is a linear subspace of H. Often, the domain dt is a dense subspace of H, in which case T is known as a densely defined operator. The adjoint of a densely defined unbounded operator is defined in essentially the same manner as for bounded operators. Self-adjoint unbounded operators play the role of the observables in the mathematical formulation of quantum mechanics. Examples of self-adjoint unbounded operators on the Hilbert space L2 are or are a suitable extension of the differential operator where I is the imaginary unit and f is a differentiable function of compact support. The multiplication by x operator, these correspond to the momentum and position observables, respectively. Note that neither A nor B is defined on all of H, since in the case of A the derivative need not exist, and in the case of B the product function need not be square-integrable. In both cases, the set of possible arguments form dense subspaces of L2R. Constructions. Direct sums is 2 Hilbert spaces Hone and H2 can be combined into another Hilbert space, called the orthogonal direct sum, and denoted, consisting of the set of all ordered pairs zone, x2 where Roman 11, high I equals 1, 2, and inner product defined by. More generally, if high is a family of Hilbert spaces indexed by I, then the direct sum of the high denoted consists of the set of all indexed families in the Cartesian product of the high such that the inner product is defined by. Each of the high is included as a closed subspace in the direct sum of all of the high. Moreover, the high are pairwise orthogonal. Conversely, if there is a system of closed subspaces I in a Hilbert space H that are pairwise orthogonal and whose union is dense in H, then H is canonically isomorphic to the direct sum of vi. In this case, H is called the internal direct sum of the vi. A direct sum internal or external is also equipped with a family of orthogonal projections I onto the if direct sum in high. These projections are bounded, self-adjoint, idempotent operators that satisfy the orthogonality condition. The spectral theorem for compact self-adjoint operators on a Hilbert space H states that H splits into an orthogonal direct sum of the eigenspaces of an operator, and also gives an explicit decomposition of the operator as a sum of projections onto the eigenspaces. The direct sum of Hilbert spaces also appears in quantum mechanics as the Fock space of a system containing a variable number of particles, where each Hilbert space in the direct sum corresponds to an additional degree of freedom for the quantum mechanical system. In representation theory, the Peter-Weyl theorem guarantees that any unitary representation of a compact group on a Hilbert space splits as the direct sum of finite-dimensional representations. Tensor products. Orthonormal bases. The notion of an orthonormal basis from linear algebra generalizes over to the case of Hilbert spaces. In a Hilbert space H, an orthonormal basis is a family at K B of elements of H satisfying the conditions. Orthogonality: every two different elements of B are orthogonal. Edge equals 0 for all K J B with K J. Normalization: every element of the family has norm 1. Ek equals 1 for all K B. Completeness. The linear span of the family K-B is dense in H. A system of vectors satisfying the first two conditions basis is called an orthonormal system, or an orthonormal set, or an orthonormal sequence if B is countable. Such a system is always linearly independent. Completeness of an orthonormal system of vectors of a Hilbert space can be equivalently restated as: if V equals 0 for all k, B and some V, H then V equals 0. This is related to the fact that the only vector orthogonal to a dense linear subspace is the 0 vector, for if S is any orthonormal set and V is orthogonal to S, then V is orthogonal to the closure of the linear span of S, which is the whole space. Examples of orthonormal bases include the set 1, 0, 0, 0, 1, 0, 0, 0, 1 forms an orthonormal basis of R3 with the dot product. The sequence f and n, z with f and x equals x swappings forms an orthonormal basis of the complex space L2, 0, 1. In the infinite dimensional case, an orthonormal basis will not be a basis in the sense of linear algebra. To distinguish the two, the latter basis is also called a Hamel basis. That the span of the basis vectors is dense implies that every vector in the space can be written as the sum of an infinite series, and the orthogonality implies that this decomposition is unique. Sequenced spaces. The space L2 backslash display style backslash L2 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 of square summable sequences of complex numbers is the set of infinite sequences of real or complex numbers such that this space has an orthonormal basis. This space is the infinite dimensional generalization of the L2 n backslash display style backslash L2n space of finite dimensional vectors. It is usually the first example used to show that in infinite dimensional spaces, a set that is closed and bounded is not necessarily sequentially compact, as is the case in all finite dimensional spaces. Indeed, the set of orthonormal vectors above shows this. It is an infinite sequence of vectors in the unit ball, i.e., the ball of points with norm less than or equal 1. This set is clearly bounded and closed, yet no subsequence of these vectors converges to anything, and consequently the unit ball in L2 backslash display style backslash L2 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 is not compact. Intuitively, this is because there is always another coordinate direction into which the next elements of the sequence can evade. One can generalize the space L2 backslash display style backslash L2 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 in many ways. For example, if B is any infinite set, then one can form a Hilbert space of sequences with index set B defined by the summation over B is here defined by the supremum being taken over all finite subsets of B. It follows that for this sum to be finite, every element of L2B has only countably many non-zero terms. This space becomes a Hilbert space with the inner product for all x, y, L2B, A. Here, the sum also has only countably many non-zero terms and is unconditionally convergent by the Cauchy-Schwarz inequality. An orthonormal basis of L2B is indexed by the set B given by Bessel's inequality and Parseval's formula. Let phone Fn be a finite orthonormal system in H. For an arbitrary vector x, H let then x fk equals y, fk for every k equals 1. It follows that xy is orthogonal to each fk, hence xy is orthogonal to y. Using the Pythagorean identity twice, it follows that let phi I be an arbitrary orthonormal system in H. Applying the preceding inequality to every finite subset J of I gives Bessel's inequality according to the definition of the sum of an arbitrary family of non-negative real numbers. Geometrically, Bessel's inequality implies that the orthogonal projection of x onto the linear subspace spanned by the phi has norm that does not exceed that of x in 2 dimensions. This is the assertion that the length of the leg of a right triangle may not exceed the length of the hypotenuse. Bessel's inequality is a stepping stone to the stronger result, called Parseval's identity, which governs the case when Bessel's inequality is actually an equality. By definition, if at K, V is an orthonormal basis of H, then every element x of H may be written as be written as written as a written as e written as e written as written as z written as written as even if B is uncountable. Bessel's inequality guarantees that the expression is well defined and consists only of countably many non-zero terms. This sum is called the Fourier expansion of x, and the individual coefficients x are the Fourier coefficients of x. Parseval's identity then asserts that, conversely, if x is an orthonormal set such that Parseval's identity holds for every x, then x is an orthonormal basis. Hilbert dimension. As a consequence of Zorn's lemma, every Hilbert space admits an orthonormal basis. Furthermore, any 2 orthonormal bases of the same space have the same cardinality, called the Hilbert dimension of the space. For instance, since L2b has an orthonormal basis indexed by B, its Hilbert dimension is the cardinality of B, which may be a finite integer, or a countable or uncountable cardinal number. As a consequence of Parseval's identity, if K, B is an orthonormal basis of H, then the map pH, HL to be defined by PHX equals X, K, B is an isometric isomorphism of Hilbert spaces. It is a bijective linear mapping such that, for all x, y, h, the cardinal number of B is the Hilbert dimension of H. Thus, every Hilbert space is isometrically isomorphic to a sequenced space L to B for some set B. Separable spaces. By definition, a Hilbert space is separable provided it contains a dense countable subset. Along with Zorn's lemma, this means a Hilbert space is separable if and only if it admits a countable orthonormal basis. All infinite-dimensional separable Hilbert spaces are therefore isometrically isomorphic to L2. In the past, Hilbert spaces were often required to be separable as part of the definition. Most spaces used in physics are separable, and since these are all isomorphic to each other, one often refers to any infinite-dimensional separable Hilbert space as the Hilbert space or just Hilbert space. Even in quantum field theory, most of the Hilbert spaces are in fact separable, as stipulated by the Weikmann axioms. However, it is sometimes argued that non-separable Hilbert spaces are also important in quantum field theory roughly because the systems in the theory possess an infinite number of degrees of freedom, and any infinite Hilbert tensor product of spaces of dimension greater than 1 is non-separable. For instance, a bosonic field can be naturally thought of as an element of a tensor product, whose factors represent harmonic oscillators at each point of space. From this perspective, the natural state space of a boson might seem to be a non-separable space. However, it is only a small separable subspace of the full tensor product that can contain physically meaningful fields on which the observables can be defined. Another non-separable Hilbert space models the state of an infinite collection of particles in an unbounded region of space. An orthonormal basis of the space is indexed by the density of the particles, a continuous parameter, and since the set of possible densities is uncountable, the basis is not countable. Orthogonal complements and projections. If S is a subset of a Hilbert space H, the set of vectors orthogonal to S is defined by the set S is a closed subspace of H can be proved easily using the linearity and continuity of the inner product and so forms itself a Hilbert space. If V is a closed subspace of H, then V is called the orthogonal complement of V. In fact, every x H can then be written uniquely as x equals V plus W with V, V and W V. Therefore, H is the internal Hilbert direct sum of V and V, and V, and V, V, and V. The linear operator PV HH that maps X to V is called the orthogonal projection onto V. There is a natural one-to-one correspondence between the set of all closed subspaces of H and the set of all bounded self-adjoint operators P such that P2 equals P specifically. This provides the geometrical interpretation of PVX. It is the best approximation to X by elements of V. Projections PU and PV are called mutually orthogonal if PUP equals 0. This is equivalent to U and V being orthogonal as subspaces of H. The sum of the two projections PU and PV is a projection only if U and V are orthogonal to each other, and in that case PU plus PV equals PU plus V. The composite PUP is generally not a projection. In fact, the composite is a projection if and only if the two projections commute, and in that case PUP equals PUV. By restricting the codomain to the Hilbert space V, the orthogonal projection PV gives rise to a projection mapping P, HV. It is the adjoint of the inclusion mapping, meaning that for all x, v, and y, h, I, h, I, h, I, h, I, h. The operator norm of the orthogonal projection PV onto a non-zero closed subspace V is equal to 1. Every closed subspace V of a Hilbert space is therefore the image of an operator P of norm 1 such that P2 equals P. The property of possessing appropriate projection operators characterizes Hilbert spaces. A Banach space of dimension higher than 2 is isometrically a Hilbert space if and only if for every closed subspace V there is an operator PV of norm 1 whose image is V such that P2V equals PV. While this result characterizes the metric structure of a Hilbert space, the structure of a Hilbert space as a topological vector space can itself be characterized. A Banach space X is topologically and linearly isomorphic to a Hilbert space if and only if to every closed subspace V there is a closed subspace W such that X is equal to the internal direct sum V. W, the orthogonal complement, satisfies some more elementary results. It is a monotone function in the sense that if U, V then V, U with equality holding if and only if V is contained in the closure of U. This result is a special case of the Hahn-Banach theorem. The closure of a subspace can be completely characterized in terms of the orthogonal complement. If V is a subspace of H, then the closure of V is equal to V. The orthogonal complement is thus a Galois connection on the partial order of subspaces of a Hilbert space. In general, the orthogonal complement of a sum of subspaces is the intersection of the orthogonal complements. If the Vi are in addition closed, then spectral theory. There is a well-developed spectral theory for self-adjoint operators in a Hilbert space that is roughly analogous to the study of symmetric matrices over the reals or self-adjoint matrices over the complex numbers. In the same sense, one can obtain a diagonalization of a self-adjoint operator as a suitable sum, actually an integral of orthogonal projection operators. The spectrum of an operator T denoted ST is the set of complex numbers L such that TL lacks a continuous inverse. If T is bounded, then the spectrum is always a compact set in the complex plane. If T is self-adjoint, then the spectrum is real. In fact, it is contained in the interval M where Moreover, M and M are both actually contained within the spectrum. The eigenspaces of an operator T are given by. Unlike with finite matrices, not every element of the spectrum of T must be an eigenvalue. The linear operator TL may only lack an inverse because it is not surjective. Elements of the spectrum of an operator in the general sense are known as spectral values. Since spectral values need not be eigenvalues, the spectral decomposition is often more subtle than in finite dimensions. However, the spectral theorem of a self-adjoint operator T takes a particularly simple form if, in addition, T is assumed to be a compact operator. The spectral theorem for compact self-adjoint operators states: a compact self-adjoint operator T has only countably or finitely many spectral values. The spectrum of T has no limit point in the complex plane except possibly 0. The eigenspaces of T decompose H into an orthogonal direct sum. Moreover, if L denotes the orthogonal projection onto the eigenspace HL, then where the sum converges with respect to the norm on BH. This theorem plays a fundamental role in the theory of integral equations, as many integral operators are compact, in particular those that arise from Hilbert Schmidt operators. The general spectral theorem for self-adjoint operators involves a kind of operator valued Riemann-Stieltjes integral rather than an infinite summation. The spectral family associated to T associates to each real number L an operator L, which is the projection onto the null space of the operator TL+, where the positive part of a self-adjoint operator is defined by the operators L are monotone increasing relative to the partial order defined on self-adjoint operators. The eigenvalues correspond precisely to the jump discontinuities. One has the spectral theorem, which asserts the integral is understood as a Riemann-Stieltjes integral, convergent with respect to the norm on BH. In particular, one has the ordinary scalar-valued integral representation. A somewhat similar spectral decomposition holds for normal operators, although because the spectrum may now contain non-real complex numbers, the operator-valued Stieltjes measure dL must instead be replaced by a resolution of the identity. A major application of spectral methods is the spectral mapping theorem, which allows one to apply to a self-adjoint operator T any continuous, complex function f defined on the spectrum of T by forming the integral. The resulting continuous functional calculus has applications in particular to pseudo-differential operators. The spectral theory of unbounded self-adjoint operators is only marginally more difficult than for bounded operators. The spectrum of an unbounded operator is defined in precisely the same way as for bounded operators. L is a spectral value if the resolvent operator 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 solvent operator fails to be a well-defined continuous operator. The self-adjointness of T still guarantees that the spectrum is real. Thus, the essential idea of working with unbounded operators is to look instead at the resolvent RL, where L is non-real. This is a bounded normal operator, which admits a spectral representation that can then be transferred to a spectral representation of T itself. A similar strategy is used, for instance, to study the spectrum of the Laplace operator. Rather than address the operator directly, one instead looks as an associated resolvent such as a Riesz potential or Bessel potential. A precise version of the spectral theorem in this case is: there is also a version of the spectral theorem that applies to unbounded normal operators. In popular culture, Thomas Pynchon introduced the fictional character Sammy Hilbert spice upon Hilbert space in his 1973 novel Gravity's Rainbow. Hilbert space is first described as a ubiquitous double agent and later as at least a double agent. The novel had earlier referenced the work of fellow German mathematician Kurt Gödel's incompleteness theorems, which showed that Hilbert's program, Hilbert's formalized plan to unify mathematics into a single set of axioms, was not possible. Remarks